So, we now know that machine learning is the process by which AI learns from data, but how exactly does this happen? There are different styles of teaching and learning, and in AI, the most used one, or the most arguable, most powerful style is called supervised learning. Hi and welcome back to the channel. This is module 3 of our series in AI literacy, and today we're looking at what is called supervised learning. My name is Lilian Shilikatata, and I will continue in this series. So as we said earlier, when we looked at machine learning, we found out that there were 3 types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. And today we're going to be exploring what supervised learning is and dive a little deeper into how it works, how it functions, and just basically use an example, an analogy to help demystify what this is, to give you a better understanding of what supervised learning is. Think of it as learning with a very clear teacher, or a highly descriptive cookbook, right? You're given examples where both the input and the correct output are known, unlike machine learning where it learned on its own. With supervised learning, you're given something with an input and an output, the correct one. This direct feedback is what allows those models to become incredibly accurate at specific tasks. So we're going to delve into how this supervised approach works and why it's so fundamental to countless AI applications today. I would indulge you, if you haven't watched the previous videos, which is machine learning and what AI is, I would advise you watch those, then come back to this concept of supervised learning and watch it. Let's continue with our concept or our analogy of using an apprentice chef, right? Or a learning chef who would be learning from labeled examples. In supervised learning, our chef gets a very special tagged cookbook, right? For every set of ingredients, which would be our input data, there's a clear and explicit label telling them exactly what the finished dish should look like, or what specific characteristics it possesses, unlike machine learning where we just gave them the ingredients to learn on its own. So, what specific characteristics it possesses? This would be our ground truth or our labeled output, right? So if the chef is learning to distinguish between healthy and unhealthy ingredients, they wouldn't just get a pile of food. They would actually get a picture of, for example, say an apple clearly tagged healthy, and a picture of maybe candy tagged as unhealthy, right? And the model learns by comparing its own prediction to the correct label. So if it predicts unhealthy food for an apple, it immediately knows that this is wrong, and it adjusts its natural parameters or its technique, right, to get closer to the right answer next time. So this constant feedback loop where the model is supervised by correct answers is what makes this approach so effective. You know, it's just like having a dedicated mentor chef constantly correcting and guiding the new chef until they master the dishes. Now, there's some, problem types within this study as well. So there's different problem or types of problems that show up with supervised learning, right? We're looking at things like classification versus regression. We're also looking at categorization versus prediction. Now, within supervised learning, there are 2 primary types of problems, as I've listed. We have classification, which is categorization, and then we have regression, which is predicting a value. Now, what do these mean? With classification, this is when we want our AI to predict a category or a class. So imagine our chef, our new chef, is tasked with sorting incoming products into a bin labeled as fruits or vegetables. Now, the output is going to be a distinct, predefined category that has been sorted, right? Now, the other examples might be like I said earlier on, is this email spam or not spam? These are 2 categories. Another one is what breed of dogs is in the picture. You give it different categories, right? And the answer is always a label or a specific group. So it's always one that is categorized and predefined, right? This is with classification and categorization. Now, with regression is basically predicting a value. And this is when we want our AI to predict a continuous numerical value. For instance, let's say If our chef needs to predict the exact cooking temperature required for a new ingredient, right? Let's say based on its weight and moisture content, for example. Now, the answer isn't a category like earlier on. It's a number that can fall anywhere within a range, right? This could be what would the stock price be tomorrow? Or how many units of a product will we sell next month? The output is always a number on a continuous scale. And many of these applications rely on these distinctions, right? Are you trying to put something into a group, or are you trying to forecast a numerical outcome? It determines whether you're dealing with classification or with the regression problem. Now, let's look at the common algorithms and applications of this, right? We will look again at our chef or apprentice chef, which we've been using as our analogy. Our chef has different tools or algorithms in their kit. So we're looking at these tools as algorithms, right? And each one is suited for different kinds of tasks. So some of those tools or algorithms you would find in supervised learning. We're looking at things like linear regression, logistic regression, decision trees, and simply linear regression is just one of the simplest used for regression problems. So imagine trying to predict, say, a student's test score, right, based on how many hours they studied. Linear regression finds the best fitting straight line, right, through the data to make that prediction. It's great for understanding very simple linear relationships. Hours studied versus what? Test score. It's making that prediction. Now let's look at logistic regression. And logistic regression is used for classifying problems, especially when you have two categories like yes or no, spam, no spam, blue, white, Despite the regression in its name, it calculates basically the probability of an event happening, and then it classifies it based on that probability, right? Just to think of it as maybe drawing a curved boundary to separate two groups. Probability of it happening and probability of it not happening. Probability of it raining tomorrow, probability of it not raining tomorrow, right? So those are the logistic regressions. Now, let's look at the third one, which is the decision trees. These are basically flowcharts, right? They're like flowcharts that help in both classification and regression. So imagine a series of yes and no questions that lead you to a decision, right? For example, let's use the example of the chef again. It could be, is this ingredient fresh? Yes or no? And depending on the answer, is it yes or no? Is it organic? Yes or no? Is it a fruit or a vegetable? Yes or no? And they're intuitive, right, and easy to understand. So if it's fresh, yes. The next question could be, is it organic? Yes. The next question could be, is it a fruit or a vegetable? Yes. And you just proceed from there, right? Just that intuitive and easy understanding of what decision trees are. I think we've seen them and usually mapped in a way. Now, these algorithms, among many others, they are just, should I say, workhouses or powerhouses that power supervised learning, right? And they solve a variety of arrays of business challenges, from predicting customer churn, which is when a customer leaves a business, to recommending personalized products, right? And then it also has its own challenges. Supervised learning has challenges: overfitting, underfitting, Bias-Variance, Tradeoff, the Goldilocks, and these are real problems, right, that you consider when looking at this. Now, let me just give you an example. Even with a great teacher, right, a chef or a learning chef or an apprentice chef, like we used before, can run into so many problems. In machine learning, we often talk about the Goldilocks problem, right, which is finding the model that is just right. Now, let's look at these issues, or underfitting. Underfitting is basically, or it happens when a model is too simple to capture the underlying patterns in a data. So our apprentice chef is still using a very basic recipe and ignoring little things but important cues, right? And then it performs poorly on both training data and new data because it hasn't learned enough. It's like just serving bland food or food that is not very inspiring. So that is underfitting, where it's too simple to capture the underlying patterns in the data. Now let's look at overfitting, which is the direct opposite of underfitting. Now the chef has memorized probably every single detail in the training data, including all the random noise or quirks that are found in it. Now they can recreate the exact training dishes perfectly. But when given a slightly different new ingredient on the recipe, it throws them off. They completely fail because they can't generalize, right? The model is too complex and has basically memorized the training data instead of learning the general rules in it. So, say a chef cooks an exact dish or bakes a cake 10 times, right? Perfectly, but you cannot adapt any new ingredient or make a slight difference if a new ingredient is introduced. Now that is overfitting. Okay, the next one is going to be the Bias-Variance trade-off. Now, this is a fundamental challenge. A simpler model has very high bias. It's consistent, right? A complex model has low bias. It can capture the simplest or the most intricate patterns. But high variance is very sensitive to the specific training data and might overfit. So the goal is to find the sweet spot, the model that balances this trade-off to perform well on new, unseen data, right? And as an AI governance professional, ensuring that models are generalized and not overfitted to specific training data is really crucial to preventing biased outcomes in real-world scenarios. Now that we've taken that out of the way, I could give you an example, right, of supervised learning in different applications. So, since supervised learning is the backbone of so many AI applications you interact with daily, I had spoken of email spam filtering, right? When you go to your email inbox, it automatically filters the spam using supervised learning. Now, let's look at medical diagnosis as well. AI models are trained on vast data sets of patient symptoms, test results, and confirmed diagnosis, right? They can classify new patient data to predict like the likelihood of a certain disease, and it's basically assist doctors in doing that. Today, machines can actually spot cancer more than doctors can do that, right? That is basically the power of supervised learning. Now let's also look at credit scoring. Banks used supervised learning to assess credit worthiness. I worked with a financial institution and worked on a team that did this a lot. They used supervised learning to assess credit worthiness, right? And models are trained on historical financial data to predict the likelihood of repayment or of loan repayment, which is a classification problem, or even the default risk, a regression problem that is predicting a score. But here it's also very tricky because if your data is biased, then you're going to get bias in your results. So you also need to be very careful. Now, with fraud detection, it's almost the same thing. Transactions are always classified as either fraudulent or legitimate based on historical patterns of the normal versus suspicious activities in this framework, right? Now, let's quickly walk through email spam detection case and how this works, right? Just an example so you understand how this is. So the first part we have is data collection. Thousands of emails are collected and manually labeled as spam or not spam. And this is our tagged cookbook, like I said initially, with our apprentice chef. Okay, the next part is the feature extraction. So the machine learning system analyzes each email, extracting features like the words used, the sender's address, the presence of certain links, capitalization patterns, certain words, misspelled emails, and all that. Then model training comes in, a supervised learning algorithm like a logistic regression, which we had talked about, or a decision tree. Remember, yes and no answers. And it's trained on this labeled data. It learns which combinations of features are most indicative of a spam. Then we have the prediction. When a new email arrives, this model basically extracts its features and uses its learned patterns to predict whether it is a spam or not. And then it takes an action, right? Based on the prediction, the email is routed to your email or is routed into your spam folder. And this elegant process really is powered by supervised learning, and it saves us from countless unwanted emails every day. So, supervised learning, with its reliance on labeled data, basically empowers AI to solve highly specific and very valuable problems, by classifying or predicting. And it's also it's the most common and most powerful form of machine learning that you'll encounter. But what if you don't have perfectly labeled data? What if you want to discover hidden patterns without knowing the answers beforehand, right? And this is exactly what we'll explore next. Unsupervised and semi-supervised learning. So we've looked at a type of machine learning, supervised learning. We also have unsupervised learning. Then we have reinforcement learning. These are the three different types of machine learning that we're exploring, and we just covered supervised learning. So in the next chapter, we're going to be looking at unsupervised or semi-supervised learning.